So the topic for today is something called Le Chatelier's principle, and it is a way to predict the direction that a reaction system will shift either forward or backward, right or left, when conditions change that disrupt equilibrium or upset equilibrium. So first, we want to reestablish that for equilibrium to be in effect, that means that the forward and reverse reaction must be occurring at the same rate. So any change that alters the rate of either the forward or reverse reaction is going to disrupt or disturb equilibrium. As a result, the system is going to try to find a new equilibrium state. And by shifting equilibrium in the desired direction, chemists can use this, this idea to improve the yield of the product they want. So basically that means that if we understand how equilibrium works and we can use it to our advantage to increase how much product we make. So Le Chatelier's principle provides a way of predicting the influence of stress factors on equilibrium systems. So Le Chatelier's principle states, if a system at equilibrium is subjected to a stress, the equilibrium is shifted in the direction that relieves the stress. So the idea is when you apply a stress to a system, the system is going to either shift to the right in the forward direction or to the left in the reverse direction in order to basically undo what has been done. And then we have to look at what kind of conditions the new equilibrium will exist at. And I have some examples to go through for that. The principle of Le Chatelier holds true for all dynamic equilibria. And so the three main conditions that we look at for disrupting equilibrium are changing pressure, which affects gases only, concentration, and temperature. So let's look at changes in pressure first. So if you change pressure of an equilibrium system, it's only going to have an effect on gases because pressure changes don't affect liquids or solids. For those changes to affect the system, the total number of moles of gas on the reactant side has to be different from the moles of gas on the product side. If the number of moles of gas are equal, on both sides, changing pressure will not have an effect. So for this example, we have 1 mole of solid on the left-hand side, so that's not affected by pressure. And we've got 1 mole of solid on the right-hand side, but we do have 1 mole of gas on the product side here. A high pressure is going to favor the reverse reaction because fewer CO2 molecules are produced. Okay, so I want to go through and make sure that we understand that. Okay, pressure is not going to affect solids. Let's just, actually, let me not do that. We're going to ignore the solids and we're going to look at 0 moles of gas on the left-hand side and 1 mole of gas on the right-hand side. If I increase pressure, you have to think about it like, oops, hold on. Where is my cursor? There we go. If you increase pressure, I want you to think about how that affects the system. What creates pressure? Gas creates pressure. So if you increase pressure, if you have a high pressure, remember what I said, the system wants to undo what you did. It wants to go back to when equilibrium was established. So it's going to move in a direction which will decrease that pressure. How do you decrease pressure? Produce fewer moles of gas. So if you shift to the left, then you're going to, okay, now of course everybody shows up. Oops. So if you increase pressure of this system, then the system wants to decrease pressure. And the only way that it can do that is by either increasing the rate of the forward reaction or increasing the rate of the reverse reaction. In this example, because you have 1 mole of gas on the right and 0 moles of gas on the left, the system is going to increase the reverse reaction rate so that you use up the gas molecules and you reduce pressure. So what's going to happen is you're going to establish a new equilibrium, but at the new equilibrium, you're going to have a higher concentration of CaCO3 because you've increased the reverse rate, and you're going to have a lower concentration of your products. If you lower the pressure in this example, let me just erase all of my, no, I can't erase anymore. All right. If you lower the pressure for this example, the system wants to increase that pressure back to what it was before. How is it going to increase pressure? It's going to have to produce more gas. More gas means more pressure. So the forward reaction rate is going to increase, and you will have a new equilibrium established with a higher concentration of products and a lower concentration of reactants. So I want you to think of this as a step-by-step process. Like if we increase pressure, what does that do to the system? The system is stressed, which means it's going to shift either right or left to reduce that stress. What was the stress for the first point? High pressure. How do we reduce pressure? We reduce the number of moles of gas because pressure comes from gas. How do we reduce the number of moles of gas? We can shift to the left, which produces more solid and uses up the gas that we have. Once a new equilibrium is established, because we've increased, right? We've increased the reverse reaction. That means at the new equilibrium, we're going to have more reactants and we're going to have less products at the new equilibrium. That means the opposite holds true for the second point. If we lower the pressure, what does the system want to do? The system wants to increase that pressure. How do we increase pressure? We shift to the right and we produce more gas. So at the new equilibrium, because we've shifted to the right, we're going to have lower concentration of reactants, higher concentration of products. Now, a real life example of this is something called the Haber process. The Haber process is how we synthesize ammonia. If you want to know why would we need to synthesize ammonia, most cleaning products contain ammonia. So it's a raw material for things that we use to clean kitchens and bathrooms and things. So this is the equation for the production of ammonia. You can see that the left-hand side of the equation has 4 moles of gas. We've got 1 mole of nitrogen gas plus 3 moles of hydrogen gas. That's a total of 4 moles of gas. And on the right-hand side, we produce 2 moles of gas. So scientists can look at this and say, how can we manipulate this equation so that we produce as much ammonia as possible? Because if you're a company that produces ammonia for, let's say, Mr. Muscle or whatever brand, Vixol, or no, Vixol is hydrochloric acid, but for the cleaning products that use ammonia when they make their recipe is the wrong word, their formula, there we go, because each brand will have their own formula. You can go to the grocery store and look at the back, the ingredients on the back. They usually list the ingredients, or the ingredients is for food. That's also the wrong word. I'm hungry. Can you tell? Like you talk about food. The components, there we go. The components or the materials that make up their particular cleaning product. And you can see for cleaning products, they always have ammonia in them, which is why you don't use ammonia and bleach together, because that produces a gas, which is very toxic. So don't do that. Anyway, so how they can manipulate this is by creating a stressful environment so that the reaction shifts to the right and produces more ammonia. So what would happen if we increase pressure here? The same thing as before. Everything here is a gas, so we have to take into consideration all of the reactants and all of the products. If we increase pressure, that means that the system wants to reduce that pressure. So it's going to shift in a direction that produces fewer moles of gas, which would be to the right. Okay, so if it shifts to the right, then you will establish a new equilibrium with a higher concentration of ammonia, which is what we want. So the equilibrium will shift to the right if we increase the pressure, because there are fewer moles of gas on the right than there are on the left. So always keep in mind that the system or equilibrium wants to reduce whatever stress you added. So it's going to move in a direction which reverses that stress. For each of the 4 molecules of reactants, there are 2 molecules of products. By making more ammonia and using up the nitrogen and hydrogen gas, the system reduces the number of molecules, thereby reducing the pressure. So new equilibrium pressure is higher because we've increased pressure of the whole system, but it's not as high as the original stress. So that means that equilibrium shifting cannot completely eliminate the stress, but new equilibriums can be established dealing with the stress. Another thing we can do is remove the product. So we have N2, and this is getting into the next, the next stress. Huh, he is here. Hold on. Okay. All right, so another thing we can do is we can remove ammonia. So we've got nitrogen gas plus 3 moles of hydrogen gas yields 2 moles of ammonia gas. So we've already established that if we have a high pressure, that means that equilibrium shifts to the right because we have fewer moles of gas on the right-hand side. And the whole point of this, if you're a company that produces, like I said, if you have a business that produces ammonia for as a raw material for other companies to buy from you to use in their formulas for whatever, then you want to produce as much ammonia as possible. So one way we can do that is by synthesizing ammonia under an increased pressure, because that creates a stress and equilibrium will shift to the right. What happens also if when we produce ammonia gas, we condense it to a liquid and we remove it? So what happens if we decrease the concentration of ammonia? The system, remember, this whole idea of Le Chatelier is the system wants to reduce or reverse whatever stress you've done to it. So if you decrease the concentration of ammonia, then the system is going to want to increase the concentration of ammonia back to what it was before. So how does the system do that? It shifts direction to the right, which means the forward reaction rate increases, which means at the new equilibrium, you're going to have a higher concentration of ammonia and lower concentration of reactants. So not only can we produce more ammonia by increasing pressure, but we can also produce more ammonia by continuously removing the gas by condensing it and then having it drip off of the distiller afterwards. So as we remove the ammonia, we're decreasing the partial pressure of ammonia. This is the same as a decrease in product concentration. So again, if we remove the product, then the equilibrium is going to shift to the right to make more product, and you can produce more ammonia that way. So that's a real life example of how we use Le Chatelier. Now, I mentioned there were 3 factors that affect equilibrium. We've already dealt with pressure, now concentration, which I just kind of touched on as well. Increasing or decreasing concentration of a reactant is also a stress on equilibrium. If we increase the concentration of reactant, as an example, this is going to cause an increase in collision frequency and therefore reaction rate. So let's just consider a general reaction. A plus B yields C plus D, which is reversible. Okay. If we increase the concentration of A, remember what I said, the system wants to reverse whatever you just did. It wants to undo the stress. Imagine it's like if you have the perfect life and then something changes and then it becomes imperfect. You're like, no, I want to go back to like when my life was perfect. Kind of like before COVID, like if we could remove COVID from this equilibrium in the world, that would be great, right? So that's what the system wants to do. It wants to reverse the effects of that stress. So whatever direction, either right or left, will result in trying to go back to the way it was, so to speak, it's going to do that. So if we increase the amount of A, the system is like, no, there's too much A. I want to get rid of that. So it's going to shift to the right to use up that excess A. But keep in mind, we haven't changed the concentration of B, C, or D. So both A and B are going to be used up faster, and we're going to form more C and D. So when the new equilibrium is reached, there's going to be a lower concentration of B because all we did was add more A. If we increase the concentration of B, same effect. It's going to shift equilibrium to the right, and you're going to reestablish equilibrium. So the new equilibrium will have a lower concentration of A and a higher concentration of C and D. So that's why I want you to think of it as like step by step, okay? If I increase B, which direction does the system want to shift? It wants to use up that excess B, so it's going to shift to the right. What does that mean when the new equilibrium is established? It means that I'm increasing the forward reaction, which means my A is decreasing and my C and my D are increasing. Sorry, that should be an arrow. What happens if I increase C or D? If I increase C or D, then the reaction is going to shift to the left. So at a new equilibrium, I'm going to have higher A and higher B. And I will have lower C or D depending on which one I'm increasing. You can also affect equilibrium by decreasing concentration. If I decrease, let's say this is like exactly like what I just described in the Haber process. If I remove one of the products as it's formed, then the system's like, wait, where did C go? I got to make more C. So it's going to shift to the right, which means, let's say I decrease C. At new equilibrium, I'm going to have lower A and B, and I'm going to have higher D. You might say, why don't I have higher C? Because I decreased it. Okay, so the main idea here, and I don't know if I'll give you homework over the weekend because you got the flower project to do. So I think I'll just have a worksheet on Monday to go through an example of how we change concentrations, pressures, and next is temperatures. Okay, this is an important point. The change in concentration does not have an effect on K, on the value of K. And you might be like, wait, why? Because if we change concentrations, it's because it's all proportional, okay? The changes have an effect on the numerator and the denominator of the equilibrium expression. So overall, K does not change. all the concentrations give the same value or the same ratio for equilibrium constant when equilibrium is reestablished. This is the important part, when equilibrium is reestablished, because you only write K, that's the equilibrium constant. Okay, right, so again, liquids and solids don't matter in equilibrium. So if you add liquid or solid, that's not going to change the concentration. You're just adding more of it. Concentration is density dependent. The density of solids and liquids is constant, regardless of how much is present. So you can't actually change concentration. You're just adding more. So let's say I have a glass of water that's 200 milliliters. If I add more water, so I've got 200 ml of water. Let's say I add another 200 ml of water. Am I increasing the concentration of the water? No, it's 100% water at 200 and it's 100% water at 400. You're just adding more. You're not changing the concentration. That's a really important point, and that's why we don't take into consideration liquids or solids in our equilibrium expressions. Okay, it's only for gases and aqueous solutions. So for example, this one, if I was writing equilibrium expression, I would write K is equal to the concentration of CO2 only. You would not include calcium oxide, you would not include calcium carbonate because they are solids. They're set equal to 1 because they don't change, so you just ignore it. Again, it's the products over the reactants raised to the power of their coefficients. Because the reactant is solid, we ignore that. Okay, blah, blah, blah. All right, and the last stress that we can put on a system in equilibrium is temperature. Reversible reactions are going to be exothermic in one direction and endothermic in the other. Some reactions which are endothermic in the forward reaction will be exo in reverse, and vice versa. So the effect of changing the temperature depends on which direction is exothermic or endothermic. Obviously, if I ask you to predict shifts in equilibrium based on changing temperature, you're going to have some kind of thermochemical information there. Just like when we did Hess's law, it could either be directly part of the equation, as in like plus kilojoules on either the left or the right-hand side, or it might be separated out as a delta H. So it's important that you remember that negative, okay, green on green is not good. Negative delta H is exothermic, positive delta H is endothermic, because I might not give you the information directly as part of the actual equation. According to Le Chatelier's principle, if we add heat, if we increase temperature, it's going to shift in a direction that uses up that heat, which means heat is absorbed. So if we increase temp, it's going to go in the endothermic direction, whichever direction that is. So like I said, if I don't give you the thermochemical data, there's not enough information for you to determine which direction it will shift. If you decrease temperature, which means you're removing heat, the system wants to add more heat, which means it's going to go in the exothermic direction. A rise in temperature increases the rate of any reaction, but in an equilibrium system, the rates of the two reactions are not equal. So the value of the equilibrium constant is affected by temperature. Okay, changing concentration doesn't affect K, but temperature does. Going back to the Haber process, it is an exothermic reaction. So one way that we can indicate that is by putting the energy that is produced on the right-hand side. This means it's exothermic. Another way that we could write it is N2 plus 3H2 and reversible 2NH3. And we could have delta H equals negative 92 kilojoules. A high temperature in this reaction is not desirable. Remember, let's say we're the owners of a company that makes ammonia as a raw material for other companies to buy from us. We do not want this this reaction occurring at a high temperature, because if it's a high temperature, then the reverse reaction is going to be favored, because the reverse reaction is endothermic. How do you know? Because going from the right to the left, you're using up energy. But we want to make ammonia because that's what we get paid for, right? That's what we sell as a product. But here's another problem. If our temperature is too low, then the forward reaction is going to proceed at too slow of a rate to be useful. We're not going to make enough ammonia. So the temperature that's used during the Haber process is a balance between the kinetic energy requirements and equilibrium requirements. We want it at a lower temperature because then that means it will favor the forward reaction to produce more product, because the forward reaction is exothermic. However, we don't want the temperature so low that the collision rate is too low to produce effective collisions. So the temperature is high enough that equilibrium is created quickly, but low enough so that we can increase our yield. We can increase the amount of product we're making. So the average temperature and pressure for this process is 500 degrees Celsius and between 700 and 1,000 ATM. That makes a satisfactory amount of ammonia. So let's just go through that again using these new data. Okay, so between 700 and 1,000 ATM, that's super high pressure. Why is it high pressure? Because if we increase pressure, again, there's 4 moles of gas on the left, there's only 2 moles of gas on the right-hand side. If we increase the pressure, we're going to shift equilibrium to the right because there's less gas on the right-hand side. Less gas means less pressure. And it turns out that even 500 degrees Celsius is a, quote, low temperature so that we don't kick in equilibrium so that it goes in the reverse direction. So this is the optimal temperature and pressure for the production of ammonia. Another example, the production of colorless dinitrogen tetroxide gas, N2O4, from dark brown nitrogen dioxide gas is exothermic. Okay, so here's our reaction. And it's exothermic, so we're going to have energy on the right-hand side. So all 3 flasks, because they are closed systems, contain the same total mass of gas. It's just going to be in different amounts of NO2 and N2O4. The temperature of this system is lowered to 0 degrees C. Remember I said it's exothermic? So we have a negative delta H. We have energy on the right-hand side. Lowering the temperature of the system to 0 causes equilibrium to shift in the forward direction. It shifts to the right. Because shifting to the right, we are producing more energy to make up for the low temperature. This allows more colorless dinitrogen tetroxide gas to form, which makes the color inside the flask a lighter brown color. This is the dark brown. This is colorless. The system reaches equilibrium at 25 degrees. At equilibrium, the system is going to have an equal amount of NO2 and N2O4. Don't know why that one didn't get subscripted, but never mind, you get it. So at 25 degrees Celsius and at equilibrium, we have a medium brown color. Again, this is dark, this is clear. If we raise the temperature to 100 degrees, keeping in mind that it's an exothermic reaction here, equilibrium is going to shift to the left. So we're going to produce much more NO2 gas, which is dark brown. If the forward reaction is exothermic, raising the temperature to 100 degrees is going to shift equilibrium to the left in the reverse reaction, because shifting left is endothermic. For an endothermic reaction, heat is always on the reactant side. So again, we have heat on the left-hand side, or we could have a positive delta H separate from the chemical equation. Increasing temperature is going to cause the value of K to increase, because if we increase temperature, it's going to shift to the right to use up that energy that's here. We're going to increase the concentration of our products. And remember, equilibrium is equal to products over reactants. So if we increase our products, it means we're increasing our value in the numerator, which means the value of K will increase. Okay, so here is a summation of the stress and what the predicted equilibrium will be. So if we change pressure, it's going to affect gas only. And it's going to shift depending on if you increase or decrease. If you increase pressure, it will shift to less gas, fewer moles. If you decrease pressure, it's going to shift to make more gas. And that just depends on how many moles are on the right or the left. If we increase the concentration of reactants, the equilibrium is going to shift to the right to form more products. If we increase the concentration of products, it's going to shift to the left to make more reactants. If we increase temperature, equilibrium will shift in the endothermic direction to use up that extra energy. And if we decrease temperature, equilibrium will shift in the exothermic direction to produce more energy. Okay, I'm going to stop there.